Hey folks, now we're going to take a look at an important structure in mathematics known as a function. And here's a very quick, kind of a user-friendly definition, may not be a real hardcore mathematical definition of what a function is. You know, I like to say quite simply a function is nothing more than a rule that assigns to each element in the domain, and we'll talk about that in a minute, one element in the range. And we'll talk about that in a minute. As we study functions, you're going to, as we go through the course of looking at functions, domain's going to be popping up quite a bit, range is going to be popping up quite a bit. Well, let's look at it. Let me draw a picture here to kind of communicate exactly what a function is. It's the first of what I call like a blob diagram. So let me make a blob here, and I'm going to say in this blob represents the domain of some function, and here's another blob which will be the range. And let me just find a few elements, and most of the time elements are going to be numbers. Let me find a few elements that are in the domain of this unknown function. Lack of creativity, I'm just going to say 1, 2, and 3. And when we say that a function is a rule that assigns to each element in the domain one element in the range, pictorially it would look kind of like this. Let's just say there's some rule. Don't know what the rule is, I don't care. There's some rule that's going to take the number 1 and send it over to the number 3. It's going to take the number 2 and let's say it sends it to the number 5. Again, I don't know what the rule is, just though I don't care. And let's say it takes the number 3 and also sends it to the number 5. So each element in the domain is going to one element in the range. That's kind of what a function would look like. I want to compare this to the following blob diagram. Let me get another blob up here. This is the domain. And here's a blob I'll call the range. I don't know where that came from. So let's say something exists that's taking the number 3, something that's in a domain, and sending it over here to the number 1. Let's say it's picking up the number 5 from the domain and sending it to the number 2. Well, let's say, just for sake of argument, that this number 3 that's in the domain also gets sent to number 3 in the range. Now check this out. This up here pictorially shows you exactly what a function would look like. Element from the domain going to an element in the range. It's okay that the numbers 2 and 3 from the domain were going to the same range element. That's okay, that's cool. Down here, this is not a function. It is not okay to have a number in the domain going to 2 different range numbers. That is not okay. It violates this definition. One element in the range. It violates that part of the definition. So this is a function. This is not a function. The best we could call this, if we had to give it a name, we'd just call it a relation. There is some relationship here. There's a relation that's taking place. But we're going to be interested in studying functions. Functions are special relations that satisfy each element in the domain goes to one element in the range. So that's a quick look at the definition of a function using what I'm going to call blob diagrams. Some people say they look like amoebas. Some other people say they look like clouds. I don't care. I'm going to call them blob diagrams. Let's look at another example. Alright, I decided to keep this definition up here of what a function is as we move to the next, as we transition into the next example. most of the time we're not going to be dealing with blobs in mathematics. We're going to be dealing with equations. And so a typical question that we need to be able to answer fairly quickly is the following. I have as an example. Does the variable y, is y a function of x? And here's an equation, negative 2x squared plus y equals 7. So it's very typical, that if you see an equation, how to tell if y, the variable y that you see, is a function of x. Very typical, and I'm going to show you what I think is a very friendly way on how to determine if y is a function of x. Quite simply, you're going to do the following. Every time you see something like this, just simply solve the equation for y. If you can solve the equation for y and get y equals a single expression involving x, then y is a function of x. If you get y equals, like two expressions involving x, it's not a function. So let's look at this first example. Negative 2x squared plus y equals 7. Solve this equation for y. I mean, it's not that difficult. You're just going to add 2x squared to both sides of the equation, and you get y equals a 2x squared plus 7. Is y a function of x? Do we have y equals a single expression? Yes, we do. When we see y equals a single expression, 2x squared plus 7, that's an expression. When we have y equals a single expression, then the answer to the question, is y a function of x? The answer to the question is yes. Y is a function of x. Okay, now, kept this definition up here. I'm going to start coming back to little pieces in this definition as I'm trying to build up to something bigger. Notice in the definition I have the word domain and the word range underlined. Generally speaking, the variable x is going to match up with domain, and the variable y is going to match up with range. We're going to see more of that here in a little bit when we start graphing functions. But I thought I'd point that out while it was up here. Hey, let's do another example of if y is a function of x. I'm going to erase the board here. I'm going to erase part A. Thought we'd do one more where you're given an equation. I'll call this part B. Same directions. Is y a function of x? I'm going to go through the exact same process. I'm going to take this equation and I'm going to solve it for y and see what we end up with. So it's not that difficult. My first step in solving for y, I'm going to subtract x squared from both sides. So now I have y squared equals 9 minus x squared. Next, I would take the square root of both sides of the equation. Now remember, when you take the square root, you have to put in a plus or minus. And that's as far as I can go on the right-hand side. I can't simplify that any further. But look at what we have. We have y equals plus or minus the square root of 9 minus x squared. Do we have y equals a single expression over here? Does y equal a single expression? No, it doesn't, because we have the plus or minus. This is saying y equals the positive square root 9 minus x squared, or y equals the opposite, the negative, square root 9 minus x squared. We don't have y equals a single expression. We have y equals two expressions. In order for y to be a function of x, we need to have y equals a single expression. Since that didn't occur here, the answer to the question, is y a function of x? For this one, the answer is Absolutely no. Y is not a function of x. So that's how you can tell if y is a function of x when you're given an equation. All right, next up in our look at functions will be something called function notation. It's important. You're going to see a lot of function notation. Here's what function notation looks like. It just simply says f of x. And that's how you would read that. You read, when you see this, you read it as f of x. Think of it as shorthand for function of x. But read this as f of x. And then here's what I'd like you to remember about this notation, this f of x notation. First off, the variable x, that is a variable, but it's the independent variable. So I'd like you to know that x is the independent variable. Then f of x, the actual, the beastie itself, the f of x, let me get a different color chalk here. F of x is the dependent variable. And I would say it's okay for you to think that f of x also represents the variable y. F of x is the same thing as the variable y. And it's okay to think that. So, quick recap. You see this? You say f of x. X is the independent variable. F of x, which is the same thing as the variable y, represents the dependent variable. And how this is going to translate itself when we start to do graphing is, when you graph, you always have a horizontal axis and a vertical axis, and you're probably used to labeling the horizontal axis with the variable x, the vertical axis with the variable y, and that's fine. It's okay to still think that, but in general, the horizontal axis is labeled with the independent variable. And most of the time our independent variable, is x. Your vertical axis is labeled with the dependent variable, f of x, or y. So that's laying the groundwork for when we start to graph these functions. It's laying the groundwork for, thinking a little bit beyond just simply x and y, but actually thinking that the horizontal axis, which you normally call x, is representing the independent variable. The vertical axis is the dependent variable. And here in a little bit, we're going to start talking about how the horizontal axis, the independent variable, matches up with the domain of a function. The vertical axis is matching up with the range of the function. That's coming down the road here in a little bit. Hey, next up, we have to get used to function notation and how to evaluate a function when we're in function notation. So that's going to be our next example. Hi, here we are. We're going to look at a quick example of how to evaluate functions. So for this example, I'm saying, let's suppose we're given the function f of x equals x squared plus 2, and we're asked to evaluate the f of 2. To evaluate a function, it's just this simple. Wherever you see an x in the function, you're going to put in a 2. So if your function of x, if f of x is x squared plus 2, and you're asked to evaluate f of 2, you're going to put 2 in for all the x's. So that would give you, put a 2 in for the x. 2 squared plus 2. Now 2 squared is 4. 4 plus 2 is 6. F of 2 is 6. Let's do another one. Let's say you're asked to find the f of negative 3. The same process. You're asked to find the f of negative 3. Repeat the process. Don't do anything different. Wherever you see an x, you're putting in a negative 3. So go ahead, toss a negative 3 in for the x's. So you get a negative 3 squared plus 2. Well, now you can simplify this. I mean, what's negative 3 squared? Negative 3 squared is 9. 9 plus 2 is 11. Okay, let's make sure we understand the process here. It's all about process. So part C, let's say you're asked to find the f of w. Don't change the process. To determine the f of w, you're going to repeat the same process that we did for f of 2 or f of negative 3. We're going to take a w and we're going to toss it into the function wherever we see an x. So put w in for wherever we see an x. So w comes in here for x and we get w squared plus 2. I can't go any further than that. It's all about the process. So how would you do this? How would you determine the f of Stewie? It's the same process. The exact same process that we've been doing. Wherever we see an x, we're going to put in Stewie. So tossing Stewie in for x, that's what f of Stewie would be. Stewie squared plus 2. It's all about the process. So when you see the following, when you see evaluate the f of x plus h, don't change what you've been doing. Don't freak out. Don't say, well, we have to do a different process. The process remains the same. However you did the f of 2, you toss 2 in for the x's. F of negative 3, you toss negative 3 in for the x's. F of w, you toss w in for the x's. F of Stewie, you toss Stewie in for the x's. To do the f of x plus h, you're going to do the same process. You're going to toss x plus h in for the x's. And that would give you, put an x plus h in here. That'll give you something like that. And you could simplify this a little bit. You could take the x plus h and multiply it by itself, so you can multiply that out to get an x squared plus a 2xh plus an h squared. And then don't forget the plus 2. So that's just simplifying down the f of x plus h. But it's all about the process. The process doesn't change. So when you see the following, this is part F, when you see the f of x plus h minus f of x, all of that junk over h, we will not freak out. We will not say, oh, well, I don't know what's going on here. It's all about the same process. By the way, this beastie that I've written up here in part H, this is called the difference quotient. It's something kind of important that keeps popping up in mathematics. But it's, how do we evaluate this difference quotient? It's the same process. We know what the f of x plus h is. We just did that in part E. If we didn't, we would compute it by taking x plus h and tossing it into the function wherever we see an x. But since I've already done that in part E, I know the f of x plus h is that junk. So let me just write that down. That's the f of x plus h. Now it says minus f of x. What's f of x? Oh, it's just x squared plus 2. I'm going to put that in parentheses to make sure I don't make a careless sign mistake. So the f of x plus h minus f of x, all of that over h, is right here. I can simplify this a little bit. Hey, notice up here I can distribute the -1. So I get x squared plus 2xh plus an h squared plus 2 minus x squared minus 2 all over h. And then, a neat thing happens. Some stuff cancels out. So, look at this. X squared minus x squared, that's gone. So, poof, poof. And then 2 minus 2, that's gone. So that's kind of cool. And let's see what we're left with. We're left with, let me pull that over here. Let me pull that up here because I'm kind of running out of room. Sorry about that. So if I pull that up here, I'm left with a 2xh plus, just an h squared over h. Alright, so we went from here to here, distributed the -1, got to here, and then noticed, hey, some stuff when we combine like terms cancel out. So we've simplified it down to this mess. Notice in the numerator we could factor out an h. And once I factor out the h, I'm going to cancel out the h. So look at what this all simplified down to. The f of x plus h minus f of x all over h, it's eventually simplified down to that mess. So to recap, evaluating a function. When you're asked to evaluate a function, you're taking whatever it is and tossing it in for the independent variable. For this one, the independent variable was x. To find the f of 2, we took 2 and tossed it in for x. To find f of -3, we took -3 and tossed it in for x. To find the f of Stewie, we took Stewie and tossed in for x. To find the f of x plus h, we took x plus h and tossed it in for x. And then in part F, we ended up evaluating this beastie that is known as the difference quotient. So we did a lot here of evaluating functions. We saw something called the difference quotient. I think next up is a look at something called the vertical line test. Alright, hey, now we're going to take a quick look at the vertical line test. Remember at the beginning of this video I had written down the definition, or a working definition of a function. To recap, hopefully you remember that it said a function is a rule that assigns to each element in the domain one element in the range. And remember I started off this video by looking at a blob diagram, what I called a blob diagram. Then the next example we did was how to determine if y is a function of x when you're given an equation. Next, we're going to look at what if we have a graph. And this is bringing us to the vertical line test, which will pictorially be the same thing as what the definition of a function was that I wrote down. Quite simply, here's my version of the vertical line test. If I have a graph and I'm asked, is y a function of x? And I see a graph. What I'm going to do is I'm going to look and see, can I draw one vertical line anywhere, one vertical line that intersects the graph in more than one point? If I can draw a vertical line, and all it takes is one vertical line, that intersects the graph in more than one point, then I do not have a function. So let's look. Which of the following, A, B, or C, are functions? So here's the graph of something in A. Looks like a nice friendly line. The question is it a function? No matter where I would draw a vertical line, every vertical line that I would draw here would only intersect this graph in one point. Because every vertical line only intersects the graph in one point, yes, this is a function. Same reason for part B. here's a graph of something. Any vertical line that I were to draw on here, any vertical line, is only going to intersect this graph in one point. That means this too is a function. Let's look at C. Remember, all it takes is one vertical line to intersect in more than one point, and boom, you are not a function. So look here and see. Here's a vertical line. Notice how it intersects the graph in 2 points. Intersects the graph in 2 points means that is not a function. A vertical, it can only intersect in 1 point. And think back to the definition of a function. Definition of a function said that a function is a rule that assigns to each element in the domain one element in the range. So that means for each x, remember the horizontal axis, x matches up with domain. For each element there, there's only going to be one y. Y, remember y is the range. Here's a value of x that has 2 different y values. So the vertical line test is just a visual way of the definition of a function that I started off this video with. So next up, I've been talking a little bit more, throughout the video so far. I've been mentioning a couple of words, domain and range. I think it's time for us to take a look at focusing more on what a domain is, and more importantly, how to determine the domain of a function. So that's the next task we're going to look at in this video. Hey folks, next up we're going to be talking a lot more about domains. It's one of the most important questions that you'll ever encounter about domain. You'll see this not only in college algebra, but you'd see it in trigonometry, Calc 1, Calc 2, just all the way through mathematics. What the domain of a function is. So a quick working definition. Here's what I kind of think of domain. Domain is, I have this function, and if someone asks me, what is the domain of this function? They're really asking me, what numbers am I allowed to put in for the independent variable? And remember, most of the time, independent variable is going to be x. But what numbers am I allowed to put in for the independent variable so that nothing bad happens? Well, what's a bad thing to happen? There are 3 bad things that you need to focus on in function land. The first bad thing is if you put in a value for the independent variable and it makes the denominator, so you say you're seeing a fraction here, it makes the denominator 0, that is bad. We can't divide by zeros. Division by 0 is not allowed. So anything that would make the denominator 0, that would not be in the domain. You're not allowed to have that happen. That's bad. Second bad thing. Say you have an even indexed radical, like a square root or 4th root or 6th root. Any value that would produce a negative number under an even indexed radical, well, that would be bad. They would not be elements of the domain. You can't do the square root or 4th root or 6th root of a negative number. You can't do it with the reals. If you bring complex numbers in and let the I guy play the game, of course you could. But when we're talking about functions, we're talking about functions of real numbers, which is kind of cool. We don't have to worry about the I guy. And then the third bad thing in function land, there's not going to be 3 bad things in function land. Right now I just have a couple question marks there. We're not going to worry about it yet. It's something that will pop up later on in this course. It's a special type of function. We will see that later on. But for right now, that's it. Let's see if we can, let's do some examples of actually determining domains of functions. So here's my first example. Typical directions, determine the domain for, and here's the first function I have. F of x is x cubed plus x squared minus 7. Okay, this is a function that, here soon we're going to be giving it a name, calling it a polynomial function. But identify the independent variable. Yes, it is x. F of x, that's the independent variable. You're asked to determine the domain. You're really being asked what numbers, from the reals, what numbers are you allowed to put in for the variable x and hopefully not allow anything bad can happen. I mean, you want to avoid bad things. Well, I don't see anything bad that could possibly happen here. I can take any real number and put it in for x, and I can cube it, and I can square it. I can definitely add them, and I can definitely subtract them. I don't see anything bad that could happen. I don't see 0 appearing in the denominator of a fraction because it's a polynomial. I don't see anything that looks like a fraction. I don't see a negative appearing under an even indexed radical because I don't see a radical. So there's nothing bad that can happen. I can put any number I can think of in for the variable x. Because I can put in any number I can think of for the variable x, the domain is all real numbers. And this is how we would write it. The domain, we will use interval notation to represent the domain, is all real numbers. That's the interval notation for all real numbers. So I can put anything I want to in for x. Let's do another one. What's the domain of the function x over x squared plus a 7x plus 12? Well, is the domain all real numbers? I don't know. I see my function here. I see it looks like a fraction. There's a denominator. I probably need to worry about some number going in for x that will end up making the denominator equal to 0. And if I allow a number to come in for x that's going to allow that will then make the denominator 0, that's incredibly bad. I can't divide by 0. So I think my task is to look and say, well, gee, are there any numbers that will make the denominator 0? Notice that's a little equation. Are there any values of x? Let me write down the denominator. Are there any values of x that will make the denominator 0? Well, that's a friendly little quadratic equation to solve. We know how to solve quadratic equations. We either try to factor it or a quadratic formula. I'm going to try to factor it, and I hope it factors because I don't really want to do the quadratic formula on this, but if I have to, I have to. This factors to x plus 3 times x plus 4. Set each factor equal to 0. And we get -3 and -4. Now keep in mind with that, these are two values of x that makes the denominator equal to 0. That means those are two values of x that are not in the domain of this function. I am not allowed to let a value come in for x that will make the denominator 0. So what I'm going to have to do is I'm going to have to write down the domain of this function. I'm going to write it down in this interval notation. I know -3 and -4 are not in the domain. They're not in the domain. So I'm going to come up here and I'm going to write down the domain. So hopefully you've digested this because I got to erase it. I need the space. And we're going to write that for this function, the domain is, now let's think about it. It's all real numbers except -3 and -4. Those are the only two numbers I'm not allowed to put in for x. So that means that all reals from -infinity to -4, parenthesis means do not include -4. Union with all real numbers from -4 to -3. A parenthesis around -3 because I'm not allowed to include -3. Union with all reals from -3 to infinity. So any real from -infinity to -4, nope, don't include -4. Union with, nope, don't include -4 up to -3. Parenthesis means don't include -3. Union with, don't include -3 all the way up to positive infinity. That would be the domain of this function. I can put in any value I want for x, except I can't put in -3, I can't put in -4, because those values of x make the denominator equal to 0. One more example of finding domains. So let me erase this. This will be part C. Not that I'm going to need all this space, don't want to freak you out, but here we are. We see an even indexed radical. Remember what I had written over here? Bad things in function land. It would be very bad for a number to come in here for x that would then produce a negative number under this even indexed radical. For example, put -5 in for x. 2 times -5 is -10. -10 plus 1 is -9. I can't do the square root of -9, not with real numbers. So I know -5 would not be in the domain. But I'm trying to determine the domain. I'm trying to determine those values of x that are allowed to come in here. All the numbers that are allowed to come in for x. I need to just remember whatever comes in for x cannot produce a negative under that square root. So I need what's under my square root. Look what's under the square root. 2x plus 1. I need that to be positive. Or it could be 0 because we know the square root of 0 is 0. So what's under the radical must be greater than or equal to 0. It must be, well, greater than 0. It must be positive, or it could be 0. Hey, just solve this little inequality. Subtract 1 from both sides. Divide both sides by 2. And hey, you found the domain. You found the domain, but now when you write it in interval notation, x greater than or equal to -1/2, that means square bracket, because you're allowed to include -1/2, up to infinity. Any number from -1/2 to infinity. Pick any number in there and you toss it in for x, you're going to get a positive under the square root and everything's good. So that's the domain of this function. So hopefully this is making some sense to you. You're doing a lot of practice of finding domains. Just remember, domain. What am I allowed to put in for the variable x so that nothing bad happens? And right now bad is producing 0 in the denominator of a fraction or producing a negative under an even indexed radical. So that's it. Thanks for watching.